Hi, I'm Dr. Colin Campbell. I'm a senior research scientist here at Meter Group, and today we're going to be talking about water potential. Many years ago, Dr. Sterling Taylor and some of his colleagues came up with water potential ranges, or comfort ranges, if you will, for plants of various types. So if you look at this table here, we have things like potatoes. I've done a lot of work in potatoes. The optimal range for water potential is -30 to 50 kPa, or kilopascals. So why would it be important to know that? Well, if you want optimum yield from your potatoes or your strawberries or even your alfalfa, you better be paying attention to putting the optimum level of water potential in the soil so the roots can take it up into the leaves and they can transpire. As they lose water, they cool themselves, they bring in CO2, and you have optimal yields. As I was thinking about this table and how delightful it is to have all these ranges here at our fingertips, like lettuce, I thought, you know what? We can really transfer this idea of plant comfort to something like a thermometer right here. Now, why would I use a thermometer? Well, first of all, temperature is something we're all familiar with, and I think you know exactly the comfort ranges that you have with temperature. For example, I really like it about 21 degrees Celsius. What do you like? It's not a big, difficult question. I'm sure you can answer that. On the other side, water potential, not water content, is the intensive variable. You can know if there's enough water available by simply understanding the water potential, an intensive property. Okay? And so I made this thermometer, kind of the idea of that temperature that shows as you get drier and drier toward that -1000 kPa level in the soil, that becomes very difficult for plants to grow. And you certainly would reduce your yield on a crop or the performance of whatever vegetation you're interested in. You notice that right here, we have an optimal range. This is where plants perform really well. Now, as you noticed, not all plants are exactly the same, but this scale, although it slides a little bit, can be applied generally like this. Plants really don't like to get up at zero water potential. Why? Because when plants are just stuck in water, they can't get air to the roots, and most plants need air at their roots. Plants like rice don't need them, they've got parenchyma, but they're the exception rather than the rule. So now we have our list of water potentials and the best areas to grow plants in according to their water potentials, the optimal area. Let's talk about ways to measure that. There are several ways to measure water potential. All are pretty challenging in their own way, and we're going to talk about them. This one right here is the WP4C that Meter sells. This we call a vapor equilibration instrument, meaning that it has a sample and it actually measures the relative humidity and calculates the water potential from the relative humidity. If you want to know more about that equation, go over the knowledge base, watch one of our virtual seminars, you'll get to know that pretty well. Now, this is a great thing to do in the lab, and I've done a lot of soil samples using this method. It's really the only way to measure water potential of drier soils. Well, what do I mean? Is it not going to work on wetter soils? That's right. It's not going to be a great use to you if you're trying to measure water potentials around plants that are in the optimum range. What would you use for that? Well, we've got a couple of choices. Here we have a liquid equilibration device. This is called a tensiometer. Tensiometers have a sealed column of air right here, and they have a ceramic tip right here. Water can flow through this ceramic tip around in the surrounding soil. When it's just stuck in water, the pressure transducer on the tensiometer just reads 0. When it's stuck in soil, and the soil is at a water potential that's less than 0, water begins to move out, and we create a tension inside this water column, hence tensiometer, and we measure that tension. It's a first principles way, meaning a direct way to measure water potential. That's the good news. There are some challenges with this measurement, but we're going to hold that for just a moment, and we're going to talk about another method, and then we're going to compare the two. The third way you can measure water potential is a solid matrix. This is a solid matrix sensor right here, the Teros 22. The Teros 22 doesn't measure water potential like a tensiometer. It uses a relationship between the water content of ceramic, and that's right in there. So this is just some pieces of ceramic, and it actually relates them to the water potential, okay? And so if we measure the water content of the ceramic, we can infer very accurately, plus or minus 10% of a tensiometer, but not as good as a tensiometer, the water content, or the water potential from the water content. We call this not a primary measurement, but a secondary measurement.